Or I will re-explain this to community for the results, but it's not a good file. I will just add a link on a shortcut.
Okay.
We are going to look for 5G, this one and this one, that are the report, and we can open them directly with Excel. And here we get all the results. It's all in a little bit strange. It's not well organized.
Okay.
And in fact, what are this value? What we got here, in fact, it's for all pressure steps. It contains the diameter of the pore.
Okay.
Because it's a kind of model, let's say, to fill a pore of this size with mercury, you have to increase the pressure, to have a difference of pressure between this pressure will fill a pore of this size.
Alright.
So we have the diameter in angstrom, and after here we have the incremental pore, the volume of the pore having this size.
Alright.
In incremental, cumulative, and express apart in milliliter per gram or in surface, considering that the pore are spheric.
Okay.
So we have all this data, and we also have other data there. We combine here it's
final result.
This is not the final result. This is experimental condition, and here there is some result. Here, for example, we have total intrusion volume, 0.3 milliliter per gram. So it's approximately the porosity, and it can calculate here the porosity and the apparent density, the skeletal density have been calculated. We can show there that it's 2.5, and the bulk density, the density of silica is 2.6. So
okay.
It's close, so it's correct. Maybe we could reanalyze the powder example with the picnometer to have the real value, and maybe we can have a change to have a better estimation of porosity. And here it's the bulk density, so the volume density, and it's 1.4. And maybe if we reanalyze the real apparent density, the real specific gravity with the picnometer, we could have a better estimation of porosity, of total porosity. And here, so this is the result, the global results, and here it's really the distribution of porosity. If the 40% of the porosity is small pore or bigger pore,
okay.
This is what we have with
the change.
Yeah.
Okay.
Usually, what I made with this stuff, it's a wall copical cut and maybe it's this way. I was supposed to have down a thing there, but I'm not sure that it's work. Oh no, it's not working. I will just have some links. You copy here the result, and it will give all the results that you can make some graph and things like that. But I do not have time with this one because it's a little bit. Here we got to remove all this stuff. To be able to draw all curves. This is the end. So here is the smaller pore is about 30 angstrom, very small. And the bigger, but there is no evolution there.
Less than, yeah.
Yeah, so it's close to be the maximum. And so now we can plot usually we draw the. Sometimes, although what we do is express the pore volume in. The incremental pore volume in percent of the total porosity. We could do this in just a calculation, but we can also do it's in graph for the curves. It's not the way. It's more for comparison that could be interesting. So if we plot this thing. With the diameter, that is. What's it? It's not. We don't see nothing because of the small thing. Usually we plot in a logarithmic scale. So here it's what I made. I don't remember. We are sorry. So it's a little bit strange. Oh, I put the incremental volumes. That's what I want. Okay, I'm supposed to have the incremental. It's not incremental, it's cumulative.
So this is the size of pore, yeah?
Yeah.
And what's this one?
This is it's supposed to be the incremental, but it's not the incremental. It's probably the cumulative, or maybe it's kind of mistake. I think there, but it seems to be cumulative and not incremental. The incremental is this one. And so we can see here it's the volume of pore having this size. For example, for each gram of materials there is maybe there. This is not so clear. there is about 5 10 minus 2 milliliter per gram of pore having this size. So by usually we mainly use this like for comparison purpose in basis for comparison purpose. For example, if we compare the result obtained with slag-based binder or Portland cement, usually the particle or the porosity is thinner for slag-based binders than for Portland cement, and we can see this with this graph, because if it's thinner, for example, the pore are thinner, we will have the curve like that. It will be there will be a gap between the two. It will be, for example, like this. So we can have the to know what is the difference between where is located, what is the size of the pore.
So, alright, for example, in this case, the pore size around 10,000, yeah? Around 9,000 or 10,000 are the most predominant pores in this.
In this sample.
So if it goes this way, it means your pores getting smaller. So your material should be more dense, with less porosity.
Usually, if it's more dense, you have higher mechanical strength.
And less porosity.
Not necessarily less porosity. You can have the same porosity, exactly the same here that is shown there, about 45%, here 44%. So it could be the same porosity, but with bigger pore. Usually the strengths are lower because there is higher.
The size of pores are higher. I got it.
It's both results are important. That's why usually we plot them in percent of the total porosity. But if we don't want it, we can just use this unit. Usually it's more angstrom. It's a weird unit. Usually we prefer to use micrometers or nanometers. And for example, I think it's about 1 micron. Because I don't remember.
Me too. I don't remember.
But it's about 1 micron, I think so. In fact, it's exactly the same kind of analysis that we make with particle size distribution. The same idea.
Exactly.
But it's not the size of the particle; it's the size of the.
Exactly.
So that's why now globally the use with the results. I will show you after how we get the result. Now what we have to do is to not the better part of the work, but probably the most
hard part, most difficult.
No, the more risky for mercury leakage.
Alright.
So we have to open the thing and screw this. What we have to do is to have one. this, and we can use some big wine.
Pores. Size of pores.
Because there is a lot of oil in this part, and we have to take some clean wipes and put it on. Ouais, je pense qu'il y en a beaucoup dans le plat. Ouais. C'est go go. Donc là on peut essuyer. We can do this to clean for the oil, and with the other end to just be sure that the metal part is tight on the. So we can just remove.
Right.
And now we go. I'm not qualified. We also do water. I need to open. Right. We remove the oil maximum. Now we go there. We will unscrew the plates at the top. And now we will just take this and slide it on the sides to have an air entry, and then the mercury drop in the platen. So this is typical. We always have a bubble here.
Okay.
And what we can do to remove, usually I put some water there to try to remove the mercury. This is a tricky part there because we got some mercury and it could leak air. But what I want is to, my sample is very short, so it will be difficult to. Because what I want is to remove the mercury, but not
the side of this,
yeah. Like this, and the other part will be in the bucket. Usually there's a lot of mercury that remain here, so we can just this way. after this we have to clean the drawing. We use the brush.
Anyway, none of these two ways are recyclable. Is that right?
This one here.
Is recyclable?
Yeah.
Okay.
We not by
yeah.
we give it to a company. We probably they increase the temperature to control. I don't really know exactly how they. That's why here we should only put mercury and all the waste in this dry. Now it's a little bit difficult because it's not so it's not enough rigid to
go inside.
Yeah. And after that we use some first I use black and white. Pas de suite mon homme, pas une goutte. Excellent. After this we will clean it with the other one or the flip. So maybe you can try the